We know that any LTI system can be represented by their constant coefficient differential equation, and by solving that differential equation, we can get to know about the response of that particular LTI system. So this is the general format of that constant coefficient differential equation. And if we set the order to be 2, in that case, that equation turns into a second order differential equation. So the basic format or the basic representation of the second order differential equation would be something like this. Why second order differential equation is important? Because we have already seen that in most of the cases, the practical electrical circuit consists of resistor, capacitor, and inductor. That makes it a RLC circuit. And while defining this RLC circuit, we end up with differential equation something like this. So as we can call them a second order circuit because their defining differential equation is of second order. In our previous lectures, we have gone through the theoretical background, how these differential equations can be solved, and we have seen examples how second order differential equations can be solved. So by now, we already are aware of the theoretical background, how these uh, differential equations can be approached and how we can solve this. And using those techniques or the knowledge, we will look at a few numerical examples of second order circuit where we will apply the theoretical knowledge that we have gathered so far in solving these practical second order circuits. Let us now look at one example of second order circuit, a numerical problem. Uh, Let us now begin with the numerical example that requires us to solve the second order circuit. Let us first read out the question. Here it says that the series RLC circuit shown in the figure, they're referring to this figure that has following parameters: the value of capacitor, inductor, resistor are given, and two initial conditions of this circuit is given here. And they're saying that the equation for the current in the circuit is given by this expression. One differential equation is also given, and they're asking us to determine the expression for both the current and the capacitor voltage. Okay. As we have one differential equation given, which is derived for current, if we solve this, we can automatically get the derivation or the expression for the current. Once we have the value of current or the expression of current, we can uh, use it to calculate the expression for capacitor voltage. We will move to that part later. Let us first focus on the expression of current. And again, look here, there are no input involved. So that means the whole solution of this differential equation will be a natural response. In the differential equation given, we can see there are some areas where they have used the expression of R, L, and C. We can replace these values with the given values. And after replacing these RLC with the given values, our differential equations get a form like this: G square IDT squared plus 6 DIDT plus 25I equals to 0. As we have already gone through the theory, we know that for natural response, we have to assume one solution, and by plugging that solution into this equation, we will get a characteristic equation. So from here, we will directly go to the characteristics equation that will look like something like this. And if we solve this characteristic equation, the solution appears to be like this. So in our theoretical discussion, we have learned that if the characteristic equation solution returns values like these complex values, in that case, the solution can be assumed in this way. So this is the expression for current for this given circuit, and we are almost at the edge of calculating the whole expression. Uh, See, there are only two missing values, that are K1 and K2. If we can calculate the values of K1 and K2, that will give us the total expression for current for this circuit. Okay. In our differential equation solving cases, we have seen that if we can come up to this, then we will need initial conditions to calculate the values of these constants. So, so now let us look for the initial conditions. And generally, if you are given a random differential equation, in that case, you will also be given the initial conditions. But for the circuit cases, we have to look for the initial conditions, and we have to create cases where we can use those conditions as our initial conditions in order to solve these differential equations. So in this math, we can see that there are two conditions given, but that will not be enough for solving our case. Using this one initial condition, we can calculate one constant from this expression. Okay, it is given that IL at 0 will be 4 ampere. So if we write the expression of current that we have calculated, K1 e to the power minus 3t. So one initial condition is given that I0 is 4. So if we replace this equation, the t value of t with 0, we get K1 plus 0, which returns the value of K1 to be 4. Now we are left with the value of K2. Okay. But the other initial condition that is given is of VC0 is minus 4, but that cannot be used to calculate the value of K2. So we need to find another initial conditions. Preferably, we are given I0, so we should look for any expression for di dt at t equals to 0. Okay. Now that we have given value given as I0 and VC0, let us now express the whole KVL of this circuit with respect to, or we will try to look at the KVL of this circuit when the value of t is just 0. So if we apply this KVL at t equals to 0, let us see how the KVL expression of the circuit look like. This, we will have one voltage drop across this resistor at t equals to 0. This would look like this. We will have one voltage drop across this inductor, that will look like L di dt, as we are assuming the t to be 0 and Vc 0. Okay. Here we can see these two values are given. The I0 is given 4 and Vc0 is given minus 4. If you rewrite this equation, we can get to see that the expression turns out to be something like this: V0 by L minus Ri0 by L. The value of V0 is obviously minus 4. Value of I0 is 4. If we set all the values, and we have some value of L and some value of R is also given. If we set all the values, we get it to be minus 20. So we have calculated another initial condition that we can use to calculate the value of K2. Then another initial condition is that di by dt at t equals to 0 is minus 20. We have at our hand it, so we can differentiate this. This will give us di dt, and if we set the value of t 0 to the di dt, that will give us uh, the value of K2. So this is the expression of it that we have calculated before. And if we differentiate this equation, this is the expression we get. And now we have at our hand the value of di dt at t equals to 0, which is minus 20. And now if we set the value of t to 0 this equation, we get some expression like this, that this term will get 0 and the term with sign will get vanished. Here we will have 1, this becomes 1, and then we get minus 3 k1, and here we have this turns into 1, here we have 4 k2. We have already calculated the value of k1 to be 4. So if we replace the value here as 4, we get minus 20 minus 12 plus 4 k2. Therefore, we get 4 k2 equals to minus 8, and k2 becomes minus 2. Now that we have calculated the value of k1 to be 4 and value of k2 to be minus 2, now we can say that we have completed the solution of this differential equation in terms of calculating the expression of current. If we replace the value of k1 here and replace the value of k2 here, that will give us the total expression of current in this circuit, that eventually is 4 e to the power minus 3t cos 4t minus 2 e to the power minus 3t sin 4t. We have another part of this question that asks us to calculate the value of the voltage across the capacitor. So now we can apply the KVL through this loop again. So that will give us ITR plus L didt plus VCT equals to 0. Now if we set the value of VCT is equals to minus ITR minus L didt, that will give us the expression of voltage across the capacitor. So that is a task given to you. You can calculate the value of the expression for voltage that is appearing across the capacitor. So that was the solution of the example that we tried to solve.